All right, well, we started. So, how do
Did it
you?
start?
Yeah.
Okay, play.
Yeah. So I think it just showed up.
I'm going through the advertisement.
Okay. I didn't know there was one.
Me neither. And now I see us.
Okay. So, just waiting for that to get started. We're back talking about this hackathon idea for um, data science-based training, where we curate the data set and present a gamified problem to some folk. So that's that's our ambition with the project, and right now we are looking at this um, Jupyterlab notebook, and we're putting together some objects and data structures that are going to help us design what we need. So right now that's been well, we've had two videos before, right? So we've built out a basic model, which is a kind of sci-fi concept where we have star systems, and the players will investigate them through a database. And this time, I guess we're going to maybe fill out some of that a little bit more and try to get some more visualizations happening. But I'm here with Chris. So say hi, Chris. I don't know whether people can hear you or not, but
Hey, everybody.
hope so. Let me know if your audio comes back to you.
Actually, yeah, I was testing the audio right now, and yeah, it seems pretty straightforward, pretty clear.
Okay, so you can hear yourself coming back.
I was able to hear myself.
Good. Okay, so yeah. So where we finished up last time, we did a scatter plot. We had to recall how to do it. We used Seaborn, which is commonly abbreviated as SNS. And we made a scatter plot of, I think it was the end condition of, oh no, this was the beginning condition of the susceptible planets of star systems to this plague that we've come up with. Okay, so
Yeah.
yeah, go ahead.
Oh, I just wanted to give some background. So, what we created so far, the code that you were seeing above, was kind of the background behind this generator of universes that we're creating. So this is an example of that universe, and the visualization that we're seeing here. We're seeing that a universe is it's a galaxy, really, and the galaxy is comprised of a bunch of different star systems that have different characteristics. What we're doing, what we're visualizing here, is not necessarily the size of each star system, but we're looking at there's a plague that we've introduced called the Banta Black Plague. It's a really interesting concept. We'll go into that a little bit later. But what we're seeing here is all the star systems in the universe that are more or less susceptible to the plague. Just to get a visual on where we might want to, as protectors of the universe, focus our efforts and our medical capabilities. So what Rob's going to walk you through is deeper into the creation of this universe that has its set of characteristics, planets that have different issues confronting them. And ultimately, what the game scenario will be is we'll actually have people who are pulling in this data, pulling in the underlying data, looking for these relationships and trends, and trying to figure out where this plague is spreading, where it's likely to spread next, and direct resources to those areas. So we'll set up where competitive teams are using data to protect the universe. You'll feel like you're on the Star Trek bridge.
Mm-hmm. Great, thank you. Yeah, that's right. So we did create, at the end of last time, we created kind of a little simulation where we run through all of the time points that we're representing and looking to spread this Banta plague through the star systems based on having one infected planet. We could try to add this time, actually I don't need that guy there, this time we could try to add a dynamic that allows transference between star systems with some frequency, so that we can attempt to have just one star system begin with the plague and actually watch it spread across neighborhoods over time. So I think that would be pretty fun, and it's also kind of the core dynamic that we really need in the game. Okay, so we've been representing time in weeks. So right now we're just building our data set, so this isn't meant to be like a real game or anything. Just through this simulation, we've got steps through the weeks, and we've had every single star system contain a seeded planet that has the plague already. And then there's a probability of infecting on each time step that is a function of how far away the other planets are. Now, right now, the distance between planets are just integers. We haven't made that very sophisticated yet, but that's relatively easy to improve. And I might even do that offline, or in a short sort of interstitial broadcast, because I don't think that's as interesting as trying to add a big mechanic like system-to-system infection. So we've got a couple of choices to make, because we don't want to necessarily loop through every single star system every time step and make a calculation. I think that we might do some optimization, but you can help talk through with me what an approach might be for this. So, if we start with one star system, we might want to make a map of all the distances to the other star systems, and those are going to be fixed. So that's something we can do one time in advance. And once we have that, we can maybe just take everything within a maximum radius and compute the probabilities of infection within some radius, so that we don't have to loop through every single system. And for testing purposes, we can make that radius really small to begin with, so that we don't spend a lot of time spinning our wheels through a lot of star systems.
Would we want to potentially basically make a function that produces a visualization, and then as we change the characteristics within the as we feed characteristics into the function, we're adjusting the map dynamically so it can see if it at the same time that we're thinking through these parameters, kind of visualize it too.
Yeah, we want to. We're coming up with some diagnostic tools as we go, so that we can see things working for us. And we had quite a lot of play last time with the infection rates in the local star systems, and this was a little visualization right here, where we were tuning the parameters so things didn't saturate too quickly with infection. So we have some goals. We haven't met those goals yet, technically, where we want to make sure that we get some form of endpoint over 5 years of time span, in terms of the number of systems that we want to have infected within 5 years. But I think we've set up some of the mechanics to make that an attainable goal pretty soon. But I think that goal will make more sense once we only have to seed 1 or 2 places in the entire universe and watch that play out over time. So I think the first thing that we need to do is we need to build this model of inter-system distance. So there's a tool called Network X, which we could try to use. We might just start maybe from scratch, just to show the kinds of things that are necessary. It's pretty simple to build a data structure that will represent the distances. And sometimes building things from scratch it's usually educational, and even if we don't use it in production, it'll be worth testing to see if it's actually faster. So sometimes with these libraries like NetworkX, they're for networks of things, and which are also called graphs in mathematics, but not the kind of graphs where you're plotting things, but a graph of nodes and vertices. And all these star systems have distances to each other. So there's a thing called a distance matrix where you represent the distance of any star system to any other star system. So you have a source and destination. The sources will be along the rows of the matrix, and the destination might be the columns, or vice versa. It's symmetric anyway. So that's a large matrix, because we have something like 1,000 positions here. So it's sometimes the case that your own data structure might turn out to be more efficient than one of these libraries. So the libraries tend to offer you a lot of extra tools to do special things, but sometimes they come at a performance cost, depending on how they're implemented. But just to give us an idea, I guess you could imagine looping through naively, right? You could loop through all of these objects, because every dot on this graph of our universe or galaxy is one of the objects that we created earlier. And if we loop through those objects that are all contained in a list, you can look for the distance to all of the other objects and store that in, for instance, a dictionary. So I think that's what we're going to start to do that naively, and to see what kind of performance we get for that. So we have a universe object here, and just so you can see, the universe is, just check that it's still defined, because I may have closed this notebook at some point. There's some lag. Not sure why. You capturing the video okay?
Yeah, I'm seeing it okay.
Okay, good. Because I'm getting messages asking me whether my stream is buffering okay.
Actually, you're coming in pretty slow. The screen is fine, but when it goes to something as fine as looking at a human who's talking, it doesn't seem like it's sufficient for that.
Oh, weird. Okay. Maybe I've got some home network issues today. Alright, I do not know what's happening on my notebook either. So I thought... Hang on a second. This thing is not feeling like it's working properly. Restart and run all, as they say. Let me just see if I can get... Let's try this again. Oh, joy. Something crashed.
Something crashed?
Maybe. I may have to shut down. I was just running this earlier today. I haven't shut it down since then, but it's timing out on me.
Perhaps when we start doing the code video through Discord, maybe we'll see a little bit less bandwidth being used if we're cutting Google Hangouts out of this loop.
Yeah, maybe. But for some reason, yeah, there's like a nasty internal error, so I'm going to shut this whole thing down. Do you think you could do me a favor on the side? Would you look up distance matrices and see if there's a library? It might be NetworkX that will give us a simple method, but it's like a network distance matrix. So let me see. I just try this. Boom. Okay. So let me start that again.
What about scipy.spatial.distance matrix? Are you familiar with
Good.
that?
Yeah, they have one now. Yeah. Yeah, I might be able to use that. All right. Firefox, what are you doing?
You want me to send that in Hangouts or Discord?
You could even put it in the
Oh,
Twitch
okay.
stream.
Perfect.
Yeah, I'm fearing that the Hangouts is possibly.
Oh, the Nightbot does not like when I post links.
Oh, great. I added you as a moderator as well.
Hmm.
Well, okay. So if you want to send it to me over the Hangout,
I'll send it over Discord because that's persistent.
okay. Sure. Oh, well. Can't change.
There we go.
Okay. Yeah, my computer is just slowing down like crazy.
Hmm.
I'm a bit concerned. Because the only thing that we're doing different this week is you're on a Hangout.
I think it's the additional bandwidth drag. I mean, I think that's one thing, but other than that,
All right.
and multiple applications.
This is kind of running through now, so let's see how we go. All right, let's take a quick look here. So, gives you an array of vectors. Okay, so I just have to form a vector of all of the pairs corresponding to the xy coordinates. Oh, is that true? No. No, it wants them separate. Wait. Matrix of n vectors. Okay. So the example distance matrix. Okay. Hang on, I'll get back to that. Let's see if this is run yet.
Can you scroll up just slightly?
On this one, or on the?
On the screen that you're on.
Let me see what you're seeing. Oh, I see.
That's locked, or
Yeah.
What's Jupyter running?
Hang on, I've lost the mic. I'm trying to make you a bit smaller so that you can stick up. In fact, since you're not next to me today, I'm going to put you up in the corner. There we go. Yeah, Jupyter's slowed down, but I think... Oh, good. It actually ran. So... Okay, we never finished that function, that's fine. I think that's it. Oh, I had to find everything. I thought I'd run all of these. Oh, I ran them out of order, didn't I? Typical. Alright, let me move this thing up so this doesn't happen next time. So, this guy, press X, and bring him up here. Okay. Okay. So I'm running this as I used matplotlib widget magic this time, and that's Also probably going to slow things down, but that does allow me to have this little toolbar down at the bottom where I can pan and, well, there's nothing to pan at this scale, but I can zoom if I draw up the box.
Learning more about Matplotlib.
Yeah, it's using the widget front end, which is just going to add a bit more lag. So anyway, let me see, what else do we need? We need...
So on the bottom right is, you're kind of blocking it off, but is that showing the coordinates of each point that you're scrolling over?
Yep.
Nice.
Yeah, it gives you a live update. But yeah, the lag is so bad, it's just slowing the whole thing down.
You'd think the lag would be bad in like a fully fleshed video game, not something that's being created in a notebook right now.
Yeah, I think it's running through the browser and doing all these other things at the same time.
Yeah.
It's possibly maxed out what it can split between the 4 cores. And it might be churning on something. Yeah, I've not seen it like this bad before. Okay, well, I can write a loop at least. So I guess we should see what this example is like, so I can adapt it. Alright, so trying to visualize what this example was assuming they really could have done with giving a comment to make it a little bit easier to interpret. So let's see. They're going from, is this a vector from 0, 0 to 0, 1? So that's essentially the y-axis. And then, or are these 2 different points? See, I feel like the first example would be to make the 2 things the same. Yeah, okay, that makes more sense. So this makes sense to me as a symmetric thing where you have the XY coordinates repeated, right? Because you want to know the distance in both ways, both forward and backwards between the 2 pairs. So the distance from 0, 0 to 0, 0 will be in the top left, and that's 0. And then the distance from 0, 0 to 1, 1 is square root of 2. Okay, so there's your distance matrix. So I guess that's what we'll use. So all we have to do then is form a list of pairs of all of the positions in the universe and then repeat that list. So for now I'm just going to do it in a dirty way and make a list. And we have a test we have a test system up here that we're going to use to introspect and help us build what we need. So I think we named it X and Y separately. Okay, so we're going to form pairs which will be sys.x, sys.y for sys in uni. Okay, so that's now of the correct format to go into the first entry of this distance matrix, if I'm reading this correctly. Now, if you notice, the whole thing is a matrix because there's another layer of... it's a matrix conceptually. It's a list. It's a nested list in Python. So I need to put in here and I'm only going to do it for the first, say, 3 systems, just because there's so many of them. I don't want to overcrowd the output so that we can read it and make sure we understand what it's doing. Okay. So, oh no, I see. They're individually wrapped. So I have to wrap this twice. So there's a wrap there and a wrap here. What else did I do wrong? How is this not? Oh, I think maybe I'm misinterpreting how it's defining this. A matrix of m vectors in k dimensions. So we're two-dimensional, and it is a matrix. This is a matrix of m vectors. That should be okay. Now, let me take a step back.
What's the list comprehension that you built look like, or did I miss that?
That's just pulling out the x and y coordinates for each system in the list of systems. And so it's making a list of
There we go. Okay.
forming those pairs. And so there's the first 3 pairs. So maybe it doesn't like them being... I'd be surprised if it didn't like them being tuples. But since I'm confused right now, I'm going to try to make it look as close as possible to the... Oh. So I'm worried that it is reshaped a certain way. Because, again, this is the trouble with providing examples where it's not fully explained what the input data is. Because it... You know, we put 3 things here, so I'm guessing this is going to work if I just put the first 2 things. And I think it's because we're misunderstanding how to deconstruct. Yeah. No, it's not, actually. Interesting. I can't see where my structure differs.
Try 0.
What do you mean?
Try setting the slicer to 0 instead of 2.
Oh, okay. Hang on a sec. Let me introspect this as well. Wait, let's put an extra layer around. Oh, oops. Yeah, I don't need this extra layer. I'm not thinking straight because it's already a list. It's already a list of pairs. So I made it a list of pairs rather than just a list of pairs.
Okay.
So that might be okay. That's why notebooks are useful. All right, there we go. Good. Sorry about that. So now we have zeros along the diagonal as you'd expect, because that's measuring the distance from any coordinate pair to itself. And then you have all the other distances. All right, so now I can make this... I don't want to display it anymore because it's going to be huge, but now I'll take out these slices. And it will take like half a second to run. Anyway, so now we have a distance matrix. So that's fine, but I still want to filter it because I'd rather not. So based on some particular, so it's 1,000 by 1,000, right? So if I pick out a system which is at say, 50, 100. Oops, I need to put a tuple in there. Oh, sorry. There we go. So that's the distance from the 50th to the 100th system. Right, it's 88 units. These are arbitrary units. I could, for instance, if I want to know what a good radius might be, I might want to know the min and max of the distances, because we actually haven't really investigated that. I mean, we have a plot of them here, so we know roughly what the scale is, right? There's like 200 units across here and 200 that way, so that gives us some idea of the scale. But if we hadn't visualized it, something that we could do is pick a position and create a vector of these guys. course, it doesn't like displaying all 1,000 of them. Wow, that is super slow.
I'm listening to both feeds at the same time. You have a really good, I understand why everybody was liking hearing the way the music sounded.
Oh yeah.
Yeah, it's a very Space Talk feel now.
Nice. Nice. Okay, so yeah, so there's a giant long list of them, right? So what we want to know is from position 1 onwards, what is the min and max of this? And did we determine that there was a describe function? No. We had to make a data frame or a series. So we'll make a series out of this guy and then we'll describe it. So the closest one was nearly 3 units away and the furthest was about 236. So that's pretty cool. Now that's just true of we just did this for one possible guy, and you could do this systematically across all of them, but they're randomly distributed. Oh yeah, that's not going to work that way. But that's going to give us just a rough idea of where we might draw the ranges. 25% of the data is within 44 units, so we might just use something like 40 as a way to filter out looping through every single system. So I guess what I want to do is I do want to loop through I'm trying to think. So I kind of want to order the distances for a given system. So let's say that the test sys index is number 100. Okay, so what I want to do is I want to find what are the closest, what are all of the systems within 40 units of system number 100. So I can take that position and that array will be all of the distances from this index, and the 100th one of those will be 0. So I'm going to put this thing into a variable called distances, and I'm going to expect that, I think, yeah. So that's the one that's 0, and I'm going to order these. So really what I should have done is put sorted. I want these sorted, but I want to know which index is which. So I'm trying to remember if argsort is built in. I think it's built into NumPy. Oh, yes, there we go. Because I want them ordered, but I want to know the order of the indices more than I want to know the order of the distances. Because if I just have the order of the distances, I won't be able to back out which systems are those close ones. So let's see, did I? Oh, there we go. There we go. Okay, so I've sorted them, so now it'll be the 0th guy. Now that's telling me it's index 100 has the closest distance, and that's correct, right? Because my test system is at index 100, and so the closest one from this entire matrix is going to be itself, and that's at index 100. Okay, so I basically just need to ignore the first one and look out from there. So if I just sample it, if I look for the first 20, right? Those are the first system indices at at the nearest distances. But I don't know how far away those are yet. So what I actually need to do is go back to my distance matrix and pull out those distances so I can filter them. I might be able to think of a more efficient way to do this, but I'm just figuring it out on the fly right now.
But because of the sorting, you're able to see each of those numbers is the name of a star system, and you're able to like knowing that it's sorted.
Yeah. Now what I want to do, I have to think. I think that I can use fancy indexing potentially and pull out just. I didn't need to. Yeah, there we go. So what I did is in one dimension, I picked my test system index, and then for the other dimension, I provided this array of indices. And NumPy understands how to do fancy indexing, which means when it sees it in this format, it will just return the values in the other dimension of D that correspond to these indices. And as you see, they are in increasing order. So that gives me a nice way to search. So what I could have done is I could have done all of the distances. All right, so this actually, so I should have renamed this distances. I could have called it arg distances, because they're not the actual distances, they're the indices corresponding to them. Okay, so now this is the actual distances. Okay. Let me think. Well, I need to filter out. This is still an array, so if we have a threshold like, if we want to say that the plague can't go past 30 units, we're calling this just call it threshold. It's 30. We want to know all of the distances that are less than this guy. I'm trying to think, because what I want to get out of this is the number of indices that I need to pull. Because I chose 21 here, right? But it wasn't until I actually looked at the actual values of the distances that I could tell how far out I'd need to go until I reached 30. So I kind of need to set up this thing where I do a test against all of the distances for 30, and I want to see the length of the array where that is true, and then the length of that array would be the index that I'd put back here, and then that will tell me all the star systems I need to consider as a potential susceptible target. Does that make sense?
Yeah. It would be interesting to, like, since we know those planets, I always go back to visualization, but could we display these planets that we're selecting at a different color around the target?
We will, but I think we're not. Well, okay, I guess we can. We can sort of show what we've got so far. That will involve doing some additional plotting up here, so I guess I think this axis object will still let me plot to it. Let's do a little test here. So my test system is of index test sys x. So I'm going to need the x and the y. And we'll make it a black circle thing. I just need to be sure that that's going to show up on the same axis. Draw. No? Oh yeah, you can't draw with that, is it? Forget how to make these refresh in different cells. Let's see if... What were the positions? So we know where to look for. Oh, well, see, there you go. It's off screen by the looks of it, right? Because the X dimension is -38. So let me put this back to home. And that's going to take a minute because of the lag.
Just out of curiosity, so the plt.show that you just called, did that adjust this chart up here, or is there's another chart off screen that it?
Yeah, because I'm using the same axes to plot on, and I just blew it because I forgot that I needed to wrap these things, otherwise it plots a line. So we now have a artifact line showing up. But yeah, it'll plot it in the previous thing, and then the show will just force it to refresh. So let's see. There we go. I'm not sure why it's plotting to -30. It's... Okay, so it's this guy. -30 something, 60 something. I'm not sure where this other one came from. I didn't replot the whole thing because it's so laggy that it'll be blank for 30 seconds. Let me try making it red this time, and hopefully we can ignore the... unless I'm doing something else wrong. I can't tell if I'm waiting or... Oh yeah, it's still working. Huh. All right, I'll let that refresh in a minute. I can keep typing down here. So I made a test comparing all the distances to the threshold, and that will, because it's a Boolean, right? You're comparing some numbers to another number, that will return you an array of Booleans. And so I often use this trick. You can, I think you have to make a list first, but you basically want to know the first false, because you know that it'll be, because they're ordered, it'll be true at the beginning, because the closest ones will be less than the threshold. And so the first place that will be a problem is when it's false, and that position is at 55. And I can show you that the distances between, say, 52 and 57, okay, they run like that. So there you go. So 52, 53, 54, 55 is the first one whose distance is above 30. See? So once I find the index of that first position of false in the test array, then I'm going to feed that back into here. Like so. Okay, and now those are all the star systems that are within 30 units of our test system. And so this will be, I'm going to say, I'll call this test neighbors. And that way I can plot them for you. Oh, there you go. So back here, ignore this black one over here for some reason. I did something wrong earlier, but there's the red one, which is our test system. And remember, this is a 2D space. This isn't a projection of a 3D space because of the simplifications we've made. So I'll just do it naively and a neighborhood index in test neighbors, because this is an array of neighbor indices. I basically need to repeat this plot for each system where the system is given by that index. And I'll color them blue so that you can see them in contrast. I'm not 100% sure if I need to show, but anyway. Oh, okay. Did I do something wrong? Did I do something wrong? Why are they all appearing stacked?
It's interesting to see how these coordinates got generated. Just curious, so why does the x-axis begin at -150?
Oh, well, you might remember when we first generated this data set, I arbitrarily chose the center to be something like 50-50.
Ah, okay.
We made Gaussian distributions with that as the mean position. So because they're Gaussian, they can go arbitrarily far in either direction, but with decreasing probability. So they're just spread around some point. But I need to check whether I'm plotting this wrong or whether I'm making some other mistake. This is possible. I just think. Oh, wait, what did I just... Did I do that right? Yes, I did. Hang on, let me check something. Did I do it again? Did I need to put... No, I don't see it. I'm not seeing what I did wrong yet. This is a different x value, so I'm not sure. I mean, it must be my plotting, right? Because these are way too far away to be within that threshold distance. So the distance matrix I trust, I think. But you see, like, just eyeballing from this position, 30 units straight down is you know, there's no way that these guys would be in that plot. So apparently I've missed something else. Let me go back and check all my parts again. I'm also not sure what's going on here because the bottom corner of this plot is throwing numbers out like I'm not sure if it's refreshing properly. I might switch to non.
Have we lost the music?
It shouldn't have done. This track might be quiet.
Okay, cool.
Some of them aren't fully mastered because they're demos. Can you hear it now?
Totally.
Okay. Yeah, I'm not sure I'm trusting this refresh because I don't know how this black one showed up over here, and I'm not sure why these are in a straight line because the x and y coordinates are clearly different. So I'm a bit unsure what's happening. I don't know if I trust the plot. So what I'm going to do, I'm going to switch to, I'm going to take away the widget because it's costing me . This is not a good ad for Jupyterlab. People are coming and seeing this for the first time because it's never normally this slow. Alright, let's plot this again.
Yeah, it seems like we have, for some reason, Jupyterlab's running slow, and then we have our bandwidth issues we're compounding that with.
Let me try it without the show for a minute, see if that comes up. Yep, there we go. See, it's plotted it twice. I don't like that. It's 38. Oh. Oh, that's weird. I must be misremembering how to plot for a single object. I think I need to, yeah, I think I'm misremembering. I think I need to provide it a list of x's and a list of y's. I thought I could do a singleton plot. I thought they changed that at some point so that it detected it automatically, but no, I think this is what I have to do. All right, let's refresh this because it will be confused. So you have to provide all of the x's in one list as the first argument to plot, and then all of the y coordinates in a separate list to this second argument. All right, negative 30, 60 something. There we go. Okay, so that makes a problem for plotting them like this because now I have to go through and pull out all the x's and y's separately, which is a real pain. I could use zip or something, but I might just do it quick. So we're basically going to get rid of the loop, and I'll embed two of these guys. Because I have to iterate through twice to pull out the x and y's separately. I don't need this anymore. Is that what I want? Yeah. So there's absolutely more efficient ways to do that. I'm just not going to get into that because it's not that important. Okay, so there is my cloud in blue as opposed to this blue-green. That's my cloud of neighbors around the red one, within 30 distance units. And you may also have to note the axes aren't the same scale. So that's why you think this would be a circle, and it is a circle in real space, but because we've distorted the axes, I didn't set the axes to be equal with this scatter plot. So it's trying to fit in the dimensions that I gave it. And so you notice this one goes from negative 150 to 200 and something, whereas this axis goes from negative 40 to 100.
So a gamer, conceivably a gamer could do all kinds of filtering on that, on what they're displaying, so they can say, okay, yeah, show me the, yeah.
Yeah, that's right. So you'd use techniques like this to, if for instance you know that the red one is currently infected, and maybe you're doing an extremely computationally costly analysis, you might want to restrict your analysis to the nearest neighbors first, because those are the highest priority ones. So we've essentially pulled out a neighborhood within that distance. So that's kind of neat. If I rescaled the axes to make it square axes, then you would see that as they would fall within a circle. And this would all be able to, you'd be able to calculate this almost instantaneously if it wasn't for the lag with me apparently streaming in and out at the same time. Yeah, we used the distance matrix. That was super handy. That cut us some, cut out some effort. And because it returns an array, it's super low overhead, right? So the network X type of library, you actually have to define nodes on a network and so forth, and that's really a lot more work, because unless the simple way would be we'd have an all-to-all network, because everything could technically connect to everything else, but really maybe a smarter way to do it would be to connect every point to its nearest neighbors within some radius. So you might even reduce the radius and make a graph out of the nearest connections, maybe within a smaller one. So you only have, say, 5 or 6, as opposed to however many this is, which is like 20 or something.
So this matrix of distances between systems, is that something that we would make available as one of the things that people can access, or how would we have the gamers be able to?
Yeah. So last time I think we talked about having potential like difficulty versions depending on the experience that the people have coming in. So if they're really experienced, then I would say we definitely don't give this to them, because it's not that hard to calculate. And you can kind of Google what to do with a distribution of spatial points, because one of the first things that you'll come across is calculating distance matrices over those points. But for an sort of more elementary one, you might have a separate data set that does have the distance matrix as a data set. We also talked about having hints, right? So you might not give it to them, but then if you see that they're really struggling and you hear that they're trying to build something like that, but they don't remember what they need to do or where to look, then we might be able to play a sort of hint card, and that might have some information about calculating one of these, or it might just give them some of this for free.
I'm going to throw out on the side. Do you know, have you ever been in a situation where somebody takes a picture of you and your eyes look closed?
Yeah, that's happened to me a lot.
It's happening to me repeatedly based on the pattern of my blinking. So I'm trying to adjust my blinking pattern. But since the feed is lagging, I want to make it look like it.
That's pretty funny. Huh. Yeah, that's an odd thing. I wonder if there's some correlation with movement, and then maybe the movement affects its ability to keep up with the compression.
Today we will learn.
But the compression is easier when you're not moving as much.
True.
Because there's fewer things changing. Alrighty, so we've built ourselves a distance matrix, and I'm going to kill some of the stuff that we don't need, and I should probably move this import to the top, because you don't really want to have imports just lying around in the middle of your notebook, because part of the idea is you want to show off at the top like a header. Oops, I totally picked up the wrong thing. There we go. You want to show off in the header what you need for your notebook. All right. So where do we get to? So we've got a smaller neighborhood now, and we can calculate. I should make that into a function, because for any given system, we want to know what its neighbors are. So I'm basically going to take this selection of statements and generalize them into a function. So I'll call it find neighbors, and we'll start with a system index, and then I will get rid of some of these things we don't need. Now I want to merge these guys, and I think, yep, Shift capital M, or rather Shift M, will merge a selected range of cells. So I've just picked those up together, and I don't need this guy at the end. Oh, I don't really need the threshold. I'll set outside as like a global threshold. That also might be something that you make as a capitalized constant for now, to show that it's kind of a system parameter or game parameter. Okay, so we're going to assume, what do I want to assume? No, I'm going to I'll do it properly. I'll expect you to feed the distance matrix. System index into universe list uni. Put these in backticks. Oh, that did not do what I expected it to.
For those that are a little bit new to creating functions in Python, Rob is creating a doc string, which is really what you should include in any function that you're creating, just so that people can, like, this is where what he's typing doesn't impact the code, but it explains what something's doing. And when you're creating a ton of functions, you can get lost in your own nicknames.
Yeah, thank you. All right, so my test sysx is just going to become sysx now. I tend to use ix for a little shortcut for index. It's a habit I just acquired. I don't know if that's a good name or not. List test. Right, so I need to do this in the right order. So I don't really need test anymore. I mean, I don't need to call this test neighbors. I need to put this at the end after I've done my test. I'm going to say that the plague infection distance threshold is a global. This is an assumption. So because it's like a system parameter or like a global game parameter, I'm kind of leaving that to be outside the function. So what else do I need to pass? I need to pass my universe. And actually, do I? Maybe I don't need it. I'm looking at what I'm doing here. What is it I want to return? So these are, I'm returning the neighbor indices right now. And I could name it as such, neighbor indices. The question is, do I return a list of objects that are the systems, or do I just return the indices and let the user of the function make that? That might be cleaner. I'm not sure there's an obvious answer to that. Because if the distance matrix is already computed, you actually don't need the objects themselves from the universe, because they've already, the data that is needed has already been extracted from them and put into D. So technically I don't need this universe at all. And I'm gonna keep this function simple. So we're not going to pass a uni as an input anymore. And that way I'm going to say outputs a list or an array actually of indices for neighbor systems within threshold distance to sysx system, something like that. So maybe wrap that. Okay, so I'm basically going to return neighbor indices. I'm actually going to, I could have put a return in the previous line, but I'm going to leave this here just so that it's a bit more readable, because that way you can see, I guess it's in the outputs part of the doc string now. So I guess I could just replace this whole thing with return, because if you're not sure what it is that you computed, you can read the doc string. All right, so we should test this function on exactly what we just did, just to make sure that I haven't missed anything weird. So I want to just call this function on my test system x with my d. And there we go. That should be the same as what we computed earlier. Did I print those out? Probably. Yes, there they are, so they're the same. All right, so the function works just fine.
Beautiful.
And all right, so now what I'm going to do, we're going to have a second. So we had a function last week that computed the infection probability, and that falls off with distance. Where did I plot that? I lost it. I probably need to replot. Where did it go? Oh, here it is. So where are my samples? Make sure I've executed these functions. Where did my plot go? Is it going to come out, or is it just wrong? It's just wrong. All right. Something. My plots aren't coming out.
98 was supposed to come out as a plot.
Yeah, I get rid of this.
Perhaps we're missing plt.show.
Well, you don't normally need it. I was stuck on widget because I can't change. Maybe I can't change while I'm running the same notebook. But in any case, that should what? Oh, that did it. There we go. Okay. All right. So we can see that it falls off with distance, right? So we could use this function as our inter-system, but we might need to rescale this distance because, well, we've got planets currently between 0 and 9 integer distances, and those aren't really on the same scale as this. This is all kind of a bit inconsistent because we've got some of these closer star systems being only, say, 3 or 4 units away, so those, I guess, shouldn't be the same distance units as the internal system distance units. So maybe we shouldn't use this function. We should just write a similar function that we can use outside of systems. So I'm going to grab this. So now this infect prob, this is going to be exclusively internal to systems. Oh. Okay, so this is what should we call this? Global or something like that. This whole universe. Okay, so now we want to make this fall off a little bit less strongly than the previous function did, because we want to make it fall off essentially so that there's a reasonable probability within this infection distance threshold and a much lower probability outside. All of this is arbitrary, I'm just making some stuff up. So let's see. So the distance now will need to be rescaled because, I mean, it's essentially the same function, we're just rescaling it. So I'm going to multiply the distance by something. So if I make the distance effectively much smaller. So let me look at this diagram, right? So I've got systems that are as close as 3 units and systems that are as far away as over 100. And I want most of my probabilities to be within 30 or so. So I guess I want the knee of this curve to be closer out to 30 distances. So whereas when I put in, say, what would this be, like 5 before, I now want that to be about 30. So if I divide my input by 5, that way I've rescaled the x-axis, and that should... So these need to be renamed because I don't want to overwrite the other ones.
That'll be interesting when we look at the 50-year data and look at the starting point and see how it's creeped across the universe.
Yeah, that's the exciting part that I want to get to. Okay, so let me take some samples of that. I'm not sure, there's a star showing there like it hasn't finished, and I don't know why. That would be so slow. But let's take some new samples and plot those. So let me grab those cells. Huh. Why is this still computing? What's happening? I think that this widget thing is somehow really busting. Oh, it's plotted it on the same graph. Yeah, something's up with the notebook. Let's try plotting it down here and see if it's insisting on plotting it on the same graph. Okay. All right. So now you can see the knee has moved out. Although because I've scaled it out to 200, it's actually not the knee isn't as far out as I maybe would like it to be. So I could make that come out a little bit further. So maybe not divide by 5, divide by 10.
And what does the knee represent?
Wait, is it doing something? Dude, why is it so slow? Apparently drawing 200 data points is enough to make this thing grind to a halt. Well, you want, in a sense, you want the probabilities to... So this is like a soft threshold, I guess. I'm trying to find a zone in which the probabilities are relatively modest size. So that this will be the red curve now. So you've got 10% chance at extremely short distances, but nothing will be that short of distance. I probably should have started the x-axis further out, but say from about here onwards, you've got a probability of about 0.02, and those probabilities get very low after some distance, which I wanted to be about sort of 30 roughly. And so the knee is just one way to think about it's the place of greatest curvature is one way to define a knee, and that's obviously going to be somewhere around where the tangent line is across here like that.
And the x here is what?
X here is distance away from the infected planet or system in this case.
And that means the probability is over what period of time? 52 weeks?
Yeah, per week.
Okay, per week, okay.
So really the nearest distance is about 3 units, so I should have probably started this range from 3. And I don't need that, I don't need 200 points, I only really need 50. But it's just astonishingly slow to run something so simple. Well, the other thing I was thinking about doing is making this background level 0. Because in a sense, we may actually want to shut off there being any transmission after some distance. So currently we have this kind of background level of probability at any distance. Right, so it asymptotes to this value, which is about 0.005. So if we want that to be asymptoting towards 0, then this C value here needs to be 0. Wow, I just don't know what it thinks it's doing. Right, I'm going to try clearing the output and see if that helps to reset the kernel.
It's a good way to look at it. And the way that I'm writing the anti-black plague into the story, it won't necessarily have to depend on trade for it to happen. So it is something that can spread throughout the universe. Or galaxy, I'm sorry.
All right, this is kind of too much. I'm just going to restart. I just can't understand why these things are taking so long. My computer's like, you could cook on it right now.
Wow.
All right, so I'm not going to change to widget. Let's try going through some of these again. Yeah, so we're going to loop through a neighborhood, and we'll loop through that neighborhood, find out the probability based on the distance within that neighborhood that there is a transmission event that's between systems, and then if we roll the die, essentially, and it's below that probability, then we will choose a random planet that's susceptible in the other system and mark it as being susceptible. And what we should be able to see is something that's a lot like models that people make in mathematical biology, where they simulate. There we go. They simulate the movement of some activity, say across the brain, or it could be the growth of mold on a substrate. And sometimes you get these sort of events that are long distance things, like the wind kicks up and it spreads the disease long distance. It's also something you might have heard of in forest fire modeling, which is where some of the theory behind these things also comes from. It'd actually be pretty interesting. Well, I guess we're designing this so that there's not too much saturation of the plague, because in forest fire models, what you see is that the tree, the land regrows, right, after a period of time. So what you find is that the regrowth allows the fire to come back around and get started again over a sufficiently long period of time if the fire isn't put out. But we should never reach a saturation point where, you know, the whole thing is basically getting filled with fire, or in this case, plague. All right, did I make a test universe? Yes, I did. I guess I did. So I'm not going to replot those right now, but I am going to. I need to recompute something else. Okay, boom, 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 boom. There we go. All right, that's better. Oops, not 50. 5. Okay, there we go. So now you can see it's beginning to asymptote to 0. So I want to maybe make... What's happening? Oh, it's plotting it against an integer. Ugh, that's a pain. Okay, let me generate my test distances. And just make a linspace object. This is a much cleaner way to do it. I'll start with 3 to 200. And I want 50. That's what I thought I was writing before. So if I make all my distances, then I can more easily reuse it. And then I'm going to plot the distances against the sum. There we go. Great. So now At the closest distance, which is about 3, there is quite a high probability. That's like a 3% chance on every single week that there'll be an infection. And as you get out to about 50, that's rapidly dropped to below 1%. And so when you get really, really far away, it's much, much less. In fact, we may go back to dividing by 5 now that we've taken away the baseline. There we go. Okay, so 30, you can see in a sense why the knee represents something useful, I think, because you've got 25 corresponding to is that right? Oh, I see. The maximum probability is still pretty low. Yeah, okay. Let me make that a bit bigger. I mean, we should decide actually for the closest systems what kind of probability we want, and maybe 1% is reasonable because we've got to compare this to the rate of transmission within a system, and you might think that between system events are rarer than ones inside of a system.
Yeah. So no doubt in my mind that the intersystem probability should per week should be much lower.
Right. Okay. So the maximum probability here is definitely maybe on a similar scale. So we need to divide down the one for systems, and that means it has to be small. So maybe make it 0.1. Okay, there we go. All right, so now there's only a 0.3% chance at the closest distances on a given week. So they are quite rare, but since we have 5 years, and we might even have more than 5 years worth of data, this might be sufficient to see some global events. So this is where I think we can do some testing.
We're just making sure. I thought we had 50. I thought we were basing it on 50.
We were doing what, at 50?
I thought we were basing the game on 50 years of data, or were you just...
Oh, maybe 50. What did I say? 5. Sorry, 50. Yeah. Yeah, so that should be enough for there to be some long-distance events. Okay, so now we can actually look at our simulation loop and think about what we did before. So what we actually had last time is we allowed every single system to have one infected planet, provided that there were planets in the system in the first place. So we kind of need to take a step back from that and pick one system and one planet to be the initial source. And then we want to see that spread over time. So I'm going to go back to putting, maybe name these better. Source position, we'll just pick planet 0 arbitrarily because they're all randomly placed. And source planet can be 0 as well. If we're going to pick the 0 planet, I just need to make sure that my universe happens to have the right... Yeah, there's 3 planets in the first system, so that works. Check that planets in the system. All right. So again, we have an array of zeros for every system. So this is the length. There are as many systems as there are entries in this list called uni, because the uni is a list of the system objects. And so we loop through time and we loop through all of the systems. We check to see if there are planets in a target system. But what we actually want to do now, instead of enumerating through all possible systems, we actually only want to enumerate the ones that are in the local neighborhood of the infected system. So the first thing we're going to do is take advantage of this function we made earlier called find neighbors, and pass in okay, interesting. So NHD is neighborhood, and that will be it'll be all of the systems in uni given by the indices returned from a call to find neighbors, where it requires the source to be that, and we already have a distance function d that's been pre-computed. And that way I'm only going to iterate through systems in the neighborhood. But interestingly, I'm thinking about, so I've got the systems, but I still need to know the distances of those systems. So actually this optimization by writing a list comprehension was actually premature optimization, because I actually want to have those distances from D. So what I really need to store are the indices into D that come from this function. Because I'm going to need, it'll be quicker for me to pull the distances out of D than recompute them. Okay, there we go. So for a system in the neighborhood, its distance will be, so if you look here, I've enumerated this neighborhood list, which means that sysnum goes from 0 to the number of systems in the neighborhood. And so if I index neighborhood indices with sysnum, that will give me a valid index into D, the distance matrix. So I want to know the distance between my source and my destination, and that's now a floating point real number, and that's my input to infected probability global. So P of global transmission is infect prob global list. Yeah. Okay. So all of that is true. All of that is moot if the number of planets there is 0, because there's nothing to infect. So I should actually move that catch further up. So I'm going to continue if there are no planets in the target system. All right, so we've got the probability, and we don't want this anymore. So now we have to, interesting. So there's different ways. So we were modeling the susceptibility of a planet based on some of its properties. So if we want to keep that going, then we are going to do something similar to what we did before, which is we were picking oxygen as just an example, and we had a threshold that if the oxygen level on that planet isn't above that threshold, then it's not susceptible to the plague. We also don't want to we don't want to reinfect it, or rather reinfecting we're going to assume means nothing if it's already infected. So if we've already marked a planet as infected, then we just don't even try to compute what's going on. So I think I'm going to make that all come later, because the first thing I really want to test is I want to see how quickly it can spread between systems without really thinking about the planets. There's just too many things to fix at once. So I'm going to temporarily dump some code in that raw cell there. Okay. But I do still want to draw a random number. And let's see, what else do I want? Actually, I think this needs to move as well. Okay, so pick a random number, And basically, if this random number is less than my threshold probability, then the transmission is successful. So I guess for now I just need a marker, just like I did with the planets. So we created an attribute called infected for a planet. I guess for now, just temporarily at least, I want to mark that the system is infected, which means I'm going to need to go back to my system object and add an attribute, which might be temporary.
So we are now to a point where we're able to identify systems that are infected based on the probability over time.
Mm-hmm.
So when we get to the visualization, are we going to show like multiple states where here's year 1 versus year?
Yeah, what I'm thinking is I'll make a function that runs the loop as past state, and I'll run it. So it's not going to be very, especially with my computer being this slow, we're not going to be able to animate it in a cool way. Instead, I'll just run it a couple of times and show you sort of manually the states at those times, and hopefully we'll see. There we go. So what I'm realizing now is that every time I remake the universe, I need to recompute the distances. So what I really want to do is I want to make these part of what happens when I first build my universe. Yeah. There we go. Okay, so, and I think this is all we'll have time to get to today. I should leave, actually I should leave here a test for next time. Okay, good. All right, so we're going to go through some number of weeks, and we're going to look at all the possible infections from one source, and we're not going to consider follow-on infections from infected planets. You know, so we're not going to look at any secondary effects. We're only going to look at infections from a single source. We just want to get that working and make sure that we even see any changes at all over the period of time. So I think this should at least tell us, it'll give us a record at the end. I actually don't need this infected array right now. I'm not using it. Okay. And oh, well, strictly speaking, I didn't need to recompute this neighborhood for every time point. That's fixed. But what might not be fixed? Well, no, I should. Yeah, let me take it out. That's bad. You shouldn't recompute things every time through a loop if they are fixed. All right. So what I should have though now is I'll just test for any of these things being true. I want to know if sys is infected for sys in uni. True. Well, I guess that would be true. Actually, no, it wouldn't, because I never set. Ooh, okay, good. I think that actually worked. So what I'm going to do now is list all of the systems that get it. Oops. If, sorry. There we go. So there's that many star systems got infected over the length of time that we simulated for, which I've forgotten how long that is. It's 260 weeks. So this was just 5 years. Okay, so over 5 years, that one system infected however many that is, 1, 2, 3, 4, 5, 6, 7 systems. So that's not too bad, because you have to remember that's going to be exponentially growing right? Because over time, each of these, we assume, is going to become a seed for further spreading. But we haven't allowed for that yet, right? We've hardwired the source to be this one planet that we first. Okay, so what we could do is we could plot which ones we found. Now notice that I never set this infected attribute on the source planet, which is going to be a shortcoming soon. So
basically, what you're saying is you never set the infection attribute to cause that planet to become a source planet.
yeah. I mean, I've hardwired it into the way this loop works, but to be consistent in the data structure, I should have marked that object to have true on that attribute, which is what I've just written in here. But that's how I knew it worked, even when I got that any statement to say true. Because for a minute I thought, oh, well, of course there's one, there's the source planet. But because I never set infected to be true on that source planet, that meant there was some other planet that was infected from this statement at the end here. So, because what I want to do, I really want to plot all of the other. It doesn't matter. I'll just plot all of them. It'll overwrite one of them. Because now, right, if I run this loop, there'll be an extra guy. Oh, actually, I didn't run it, did I? There we go. So there's an extra one now because I set the source one. All right, so infected, neighborhood, systems is whatever the output of that is. And now I can go back to my plots and I can plot the system, or rather the universe, and get rid of this. I'm going to plot the so for system in, so these are actual system objects. I'm going to do something like I did before, which is plot the system X against the system. Oh, yeah, that would be more efficient. I'm actually going to reuse. I'm going to reuse that whole structure. So sys dot X in that comma sys.y, make those blue again, and then we know that we made the source 0 arbitrarily, so I'm just going to pop 0 in here, and we don't need that show anymore. Or maybe we do, I'm not sure because I've changed from the widget. Great, I might have to go back to widgets because I'm not sure I can re-plot. Not letting me reuse the... Sometimes you have to put it in the same cell for it to use the same axes. There we go. Okay, so I can't zoom this. Well, I suppose I could try this. Yeah. So I'm zooming in a little bit. You can see the red one is the source planet, and you can see a collection of dark blue planets around it. So those are the ones that got infected. And you can see others that didn't get infected, which are definitely closer than the ones that did. So within just 5 years, we've got that many infected. Okay, so we could take this on exponentially, and the only thing we haven't accounted for, and this is because of the sophistication level we've assumed for the spread of the disease, you know, there might be an incubation period.
I'm getting a network error for the live stream.
Ah.
So it's just showing black.
Okay.
Hit play again, see what happens.
I mean, it thinks it's still streaming.
Oh, it got us back. Okay,
Yeah,
cool.
sorry for that's lagging. Okay, so what was the last thing that you think we just basically plotted this neighborhood to see that there was some infected over 5 years. Do you think we missed anything else?
I think that gives us a good example of the game mechanic. This is stuff that we can start. Next week we can think about how fast we want a disease to spread across systems versus within planets, or what impacts the speed of the spread. Basically, like if a system has multiple planets infected, does it make nearby systems even more susceptible? So really interesting to see that probability play out, and especially as it goes across the entire universe. Will our protectors be able to identify these planets in time to prevent the spread?
Yeah. So like I said, we could potentially build in an incubation period so that these ones that do get infected have to wait a few weeks before they're ready to infect again. Right, because an infection has to spread locally once it arrives. So it might be fair to say that the infection needs a while for it to get strong enough that it can transmit between systems again. There's also the idea that, you know, if multiple planets become infected within one system, maybe that scales up the chance of that whole system infecting another system.
Yeah.
Right, so we have to account for some of those things for it to be a bit more realistic.
Give it time to fester up.
Yeah, but for just today, because since we're going to be running out of time shortly, I'm just going to change the neighborhood that I used down here at the end, just to show you, because I restricted this plot to be, or restricted the infection to be within that neighborhood that I computed of 30. But I also created this probability distribution to behave in a similar way, this one. So I guess what I'm going to do is I'm actually going to let it go out to, say, a distance of 100, and you should still see that most of the things that get infected are within a short distance. So let's see. Oh, that's right. Then I'm just going to change my threshold. I'm going to change that to, say, 100. And that's a global, so that will affect what happens when the neighborhood function is called. So let's run that loop. It took a moment longer because it's had to go through more neighbors, and then I'll replot this whole thing. There we go. All right, so now you can see there are some much further outliers. There's three or four about here, and there's one here and another one down here. Okay, but you can still see most of them are clustered down here. So we can continue to tune those parameters so that, you know, we can kind of restrict this suitably. Over 5 years, that's potentially still quite a lot of spreading.
Could be interesting if we have characteristics that maybe one system doesn't infect other systems unless there's some certain characteristics there. So where you have a red as a seed planet, potentially there's only a probability that there's another planet that can actually function as a seed planet.
Yeah, there's going to be a whole host of things. Because we haven't checked for the susceptibility of these systems. We've only checked the minimum condition is that they have a planet, because some have no planets. But yeah, we also have to check that there is a non-infected susceptible planet based on some threshold like the oxygen level. So that will reduce this a little bit.
Yeah.
Because there'll be a lot more planets that aren't susceptible. But yeah, that's tuning. We've got the basic mechanic down. And, you know, maybe it's something that I'll do between now and next week, because it's really just a combination of things that we've done today and last week, is just to put those two mechanics into one loop, and then I'll just review that loop next time, and that way we should have some minimal model of spread between both planets and systems. Yeah, I guess that's more or less a good summary.
Good stuff.
Yeah. So I started putting up the videos on YouTube. So I have a YouTube channel called Transient Dynamic as well, and because the videos expire after a while, and I think this is the kind of thing that you absolutely need to be able to see from the beginning if you come in midway. So I've linked to it in the channel description on Twitch, so that you can go check out the old videos once they start disappearing. And this one will be up probably today or tomorrow.
All right, sounds good.
Yeah, so thanks very much. That was fun. And we'll chat soon. Do you want to say anything?
Yep. I hope you guys enjoyed seeing this universe being created and seeing us spread disease across it. Such is the nature of man.
Thanks, Chris. All right, we'll hang out soon.
All right, see you soon.
Cheers. Bye-bye.